So first of all, thanks a lot for attending. I'll be speaking about Project Reactor. So if for some reason you thought that I'll be speaking about Simpsons and making fun jokes about Simpsons and that's all the talk, so that's not true. You still have time to change the room, but if you're really into Project Reactor or want to learn it and know how to debug and how to live with Project Reactor, then this talk is for you. And I've been asked to share this information because apparently not everyone knows, but every question you want to ask, you can ask at slido.com, and then later after the talk, we'll go through the questions, and I'll be asking the top voted ones. So please ask your questions at slido.com, room 12, and hashtag GeeCON 2019. So, a few words about me. Who am I and why I'm talking about this topic, actually? Well, I work for Pivotal, work on Project Reactor, and things I'll be presenting were partially developed by me, and I'm really happy to show them to you. I'm organizing Berlin Spring User Group, co-organizing it. So if you're around in Berlin, just come by and listen some cool stuff about Spring. And I'm also Test Containers co-maintainer. If you know what Test Containers is, cool. If you don't, on Friday, I'll be giving a talk about Test Containers and the latest developments in the Test Containers space. Personally, I'm really into developer tools, as you can see, because Test Containers is also a dev tool. It's the easiest and the happiest way of developing for me because I know what I'm doing, I know why I'm solving problems, and I'm happy to see that I solve problems others having, and these problems most probably will be the same as I have. And despite the fact that I love the development tools, I spend most of my time doing products, high-performance microservices, blah, blah, blah. Anyways, so my first experience with Project Reactor and reactive programming in general most probably was almost the same as yours. So I had no idea. Okay, in my case, it was like this. So I had no idea what I'm doing. So yeah, it looks fancy, everyone is talking about it, but well, what should I do? I started looking at the documentation. Unfortunately, not everyone does that, but I did. And after reading the documentation, I discovered that there is mono from Runnable. Oh, cool. I mean, I'm a Java developer. I know what Runnable is. I can run some code. Yay! So I took mono from Runnable. And unfortunately, it was like, why didn't you work? What happens? Like, okay, I did everything I could. I have Runnable, I have mono from Runnable, it's perfect. Why doesn't it work? Any other framework would execute my Runnable, so what happens? This is how I discovered that in reactive world, you have two stages. One, to create something, to define your chain, your processing chain, and you need to subscribe on it. And there is a big difference between hot and cold publishers, which I will not be talking about, but until you subscribe, nothing happens. That was a bit of war moment for me because, well, I did not expect it, and who would? But actually, this separation of assembly time and execution time gives us a lot of flexibility and a lot of great features we could not achieve otherwise. So everything is kind of lazy by default. So 1 week after, I was like a reactive seer. I was quoting famous persons about reactive programming, about functional abstractions. I was, going to lunch with my colleagues, and I was talking about reactive programming. They were hating me, so I started going to lunches alone. But anyways, I was enjoying what I learned. But another week later, week of production, picture of me changed to something like this. Apparently, what works well on my machine and what looks nice in general, and everyone is talking about reactive programming as being super efficient, super fast, and flexible, and all these fancy words. When you run it in production, you must be careful and must know things about it. And it's not about writing code, actually. It's about keeping the code running somewhere. Let's talk a little bit about what could go wrong. When people talk about reactive programming and why it's bad, they usually start with the stack traces and exceptions. And it's indeed one of the most popular issues with reactive frameworks. And I'll explain why. Let's say we have this code. Classical code, we have something, we apply some operators, we run it on some scheduler, in this case, our parallel scheduler, and we subscribe on it. Okay, cool. Now, if we run it, we will see the following exception. First of all, it's large, but oh well, that's Java. Just get used to it. But if we focus on the most important part, or the part you look at first, we'll discover that apparently we don't know which source it is, or let's say, where is my package? I mean, I have this code defined in com example demo, but if you go one by one, there is no add com example demo, whatever, in the stack trace, and many other questions we would have. So, to explain why it is so, we need to focus on the assembly versus subscription, as I already mentioned. And in our case, when we do the assembly phase, when we call the operators on our reactive types, let's say we have flux range. Okay, cool. Now we apply the filter. Now we apply more and more operators. At this stage, nothing happens, really. We just predefine how it's going to be processed. So yes, we are running the operators, but as I said, everything is lazy. So we need to subscribe on it to start the processing. And when we subscribe, then we go from bottom to up. Unfortunately, in the current set of emoji, there are no emojis for reactive types. So I think this kitty will be our subscriber. So anyways, this kitty goes to mono-subscribe on. Then mono-subscribe on will schedule it on some other thread, in this case parallel 1. Then goes through the operators we have, the other operators we have defined. And now we need to handle the subscription. Same thing with emoji, so okay, this fish will be our subscription. Anyways, now once flux range is ready to produce something, it should let the downstream chain know that, okay, I have something, I have subscription. So now this subscription goes back to the publishers. Boom, boom, boom. It reaches the subscribe call. And now subscribe call will request something. Most probably, especially if you are in this room, you heard about backpressure at least once in your life, especially if you attended the great talk by Josh earlier today. So this .request is actually what makes the backpressure work. We just tell it how many items we are ready to process. In our case, we were using just subscribe, so we just request maximum values you have, and it goes back down to the flux range. Okay, oh cool. By the way, as you can see, everything happens in the parallel thread, not in our current thread. We were composing our flow. And now we start getting the elements. So we get, flux range first will produce 0. Okay, all good here. Now it will produce 1, and it will go to flux filter. Cool, yeah, we just filter, we don't care. But then, when we pass this signal to mono single, it will raise an exception. As you can see, the exception will happen in different thread. And we have no trail to the original code who created this flow. We have to deal with it. we don't know who built this pipeline. We only know how this pipeline failed to execute. So what can we do? Let's do a short demo and check what Reactor provides to us to overcome it. Can you see it clearly? All good? Oh, good. So I have a very simple application just for the demo. And we have an endpoint. And from this endpoint, we return a pipeline which transforms into mono with a .single operator. And we subscribe on parallel scheduler. So the same kind of example. If you run it, and if we query the endpoint, we'll see the stack trace in the log. As you can see, and as we have seen before, there is no package from my application. So my application is COM example demo. Now imagine an error happens in production, and you're like, OK, cool, but I would like to know what actually happened and where it happened to fix it. So one thing you can use, not in production, but during the development, is a hook in Reactor core. It's called hooks on operator debug. And what will happen? Every time you apply an operator, now it will capture the call site where you apply it with the stack trace, because it can extract the call site from the stack trace. And now it will add this information to the publisher. Now, when an error happens, the publisher can add this information to the exception and say, yeah, this error happened at this place, so do something about it. If I restart my application and do the request again, much better. Now we see where it happened. It's a demo application, 28 and 29. But not just that, we also see the underlying processing parts from Spring Framework. So that if something happens in the Spring, you will also see that, OK, an error happened when you were processing a request, and for example, it failed to send headers to the response, or some other type of error. But as I said, this hook should not be used in production. It will dramatically affect your performance, and the latency will be much bigger, because every time you apply an operator, let's say I write, I don't know, dot map, and I do something with the item, even some simple ones, it will take the stack trace with new exception.get stack trace or stack walker on Java 9, and it will record this information. I have news for you. Stack traces are slow in JVM. That's the fact, and we have to deal with the fact that there is no easy way of capturing the call sites. And what's even worse, if your application is perfect, it never fails, there are no errors in your application at all, we still have to capture the call sites every time you apply an operator. So it's super inefficient. And for a very long time, it was the only solution you can have. Or actually, that's not true. For the production, we also have another solution. It's called checkpointing. And you can put checkpoints in your code, let's say after single. And now if we remove the debug operator, because, well, it's slow, and we run our application, sorry. Yes. We will not see the full backtrace, but at least we see that the error happened at after single checkpoint. And checkpointing is fast. You can use it in production. It's just to meet the information in your pipeline, and you don't have to worry about the performance. But I would be worried if in my code everywhere I would have to put this dot checkpoint, some random string. It will be copy pasted from one place to another, and eventually it will become a nightmare actually, because it's not only making your code bigger, it's also error prone because you have to define this checkpoint. This is why we created a tool. It's not in Reactor core, it's Reactor tools, and it is an experimental tool, but nevertheless, if we, instead of on-operator debug, use Reactor debug agent init. As you can see, I'm running these commands before my application so that they capture everything in my application. So now, if I add this Reactor debug agent init, now we see kind of the same backtrace. We see our code, but instead of doing it every time we apply an operator, we instead instrument your code with bytecode instrumentation. And if you think that bytecode instrumentation is scary, is complex, is slow, or anything, just think that any APM out there will be doing the same. So we applied the same mechanism as the APMs are doing, like AppDynamics, New Relic, and others, and we instrument the code now. And as you can see, it's not just the stack trace. We also have the checkpoints here. Every time you return a mono from some method without calling an operator, we checkpoint it too. So that if you have a chain with, let's say, web client, and you have body to mono or something, then you're not applying an operator, and your code will not appear in the result. But with this checkpointing, it will be there, and you will see this body to mono, even though it's not an operator at all. How it works? Well, I would ask the same question too if I'll be running something in production. Imagine we have this same chain, the same flow. Now, every time we call an operator, we add, so it's not the real code, but actually it kind of is a real code. We add this static dot checkpoint call. It uses some internal APIs, this is why I simplified it to checkpoint. But the idea is the same. So we're kind of putting the checkpoints for you so that you don't have to go through your code and put it everywhere. We do it automatically. And thanks to the instrumentation mechanism, we know the location of the code where it happened. So we know the exact file, we know the exact method, and so on and so forth, without doing it at runtime. So we move it to the instrumentation time, and you can also apply it with compile time bytecode transformation, so that you can pre-compile your code. Why I'm saying that it's production ready? Because checkpoint is nothing but a proxying operator, and yes, it will add a little bit of overhead to your application, very small one, just because you add one more operator and you allocate one more object. But we did some measurements, and it does not affect the 15th percentile. At least there is no notable difference, and it affects the slowest code just a little bit. So it's really that fast. Yes, so these demo outcomes. You can use dot checkpoint if you are not into Java agents and stuff. Also note that you don't need to attach this agent to your JVM. You can just call reactor debug agent.init, and it will self-attach to the running JVM. You can read on operator debug, or you can use it in testing, in your tests. But in production, or just in general, I would highly recommend Reactor Debug Agent. And we will be adding more features you cannot achieve with runtime, but you can because you know it upfront. And you can also read a great blog post by Simon, one of Project Reactor core developers, about subscription versus assembly versus subscription difference, because it's really important to understand, and you have much less questions about why it is so when you finally understand that, okay, we first define and second we execute. So, second thing, blocking calls. That's even more interesting, and it applies to any async programming, not just to reactive programming, and not just to Project Reactor. And I also want to see that if you ever took a thread dump from your running production instance, and if it looks like this, you have serious problems, believe me. So please make sure that your thread dump doesn't look like this. Doesn't matter what kind of application you're running. And I'll explain why. In Reactor, we use schedulers to schedule tasks for the execution, and how it works. Well, we have default thread pools. You can also wrap your own thread pool with scheduler interface, but the built-in ones are parallel, which is just a thread pool of n, where n is number of CPUs you have. Then you have a single scheduler. Well, it's self-explanatory, just a single scheduler, singleton scheduler, let's put it like this. And we also have an elastic scheduler, which will add more threads or create more threads if the other threads are running some workload, and it will apply some TTL and destroys them after a timeout. The thing is, when you have something like, let's say, delay or anything else, so who knows which scheduler is being used for this mono.delay call? Anyways, it's parallel. Parallel scheduler is being used, and every time you implicitly call some delayed or deferred method, it will use the parallel scheduler by default. And it's something important to keep in mind, because if you have everything non-blocking, that's cool. You have tasks, you have more tasks. You have more tasks, everything is green, everyone is happy, the emoji is happy, all good here. Now, if we have some blocking calls in our application, it's not that good and doesn't look good, because now we have some long-running tasks scheduled on our parallel scheduler, and as you can see, we have in this case only 4 rails. That may be some container running in the cloud with 4 CPUs. It can be even lower. Now we have more tasks scheduled, more blocking calls, and some other blocking calls. Now we get one task that says, okay, I want to run 4 GDBC queries, and boom. And this is bad. You know why this is bad? Because now no more tasks will be scheduled while these blocking calls are running. And imagine you have something like a web framework running on the parallel scheduler and accepting requests from your users. And just because you wanted to run 4 blocking methods in the parallel scheduler, no more requests will be accepted. So not a good thing, right? How can you fix it? Well, obvious answer is do not use blocking APIs, right? But unfortunately, it's not possible yet. There are some developments also for the GDBC style access, which is called R2DBC, but it's not there yet, so we have to deal with it. So use custom thread pool. Seriously, why not? Just offload your blocking computations if they are unavoidable to a custom thread pool. Now, when we receive a task and this task says, okay, run 2 blocking calls, boom, they go to custom 1, custom 2. Now we receive another task, they wait for the completion of these tasks, and they continue with more tasks, and more and more. Nice. as you can see, now we no longer block the main thread pool, but a separate one. And you still may have an issue if all your workload is blocking, because as you can see, there will be a slight delay between your task and the execution. And if everything is blocking, it will eventually run out of memory because we need to store the tasks somewhere, right? But if you have some blocking codes, then you can move them to a separate thread pool. Why not? So let's do a demo. And it's on another screen. Oh, super. Never happened to me. Perfect. Good. So I'll stop the application, and I'll start this code. What this code does, pretty simple one. We just start some range of numbers, and we start from 0, and we count up to the number of processors we have on this machine. My machine has 16 virtual cores, so we'll be counting from 0 to 16. We subscribe on the parallel scheduler explicitly because we want to demonstrate what happens. And we map every item into blocking code. And this code is blocking because this ledge await will block until someone calls ledge.countdown. And we also delay every emission by number multiplied by 100, and we unblock the ledge after it finishes. So raise your hand if you think that this code will execute in 1 second or less. 5 seconds or less. Nobody cares. OK, I will explain you. Let's run this code and check how long it takes to execute it. Well, unfortunately, I don't have enough time. Well, we have 23 more minutes, but if we'll be waiting 23 more minutes for this code to complete, it's not going to be a good demo, right? But what actually happens is our code blocks forever. And if we take a thread dump, then we see that all threads are parking. So parallel 2 parking, 3 parking, blah, blah, blah. They're all waiting for something. And what happens here? We schedule 16 tasks with monad delay, and we say execute them on parallel processor, parallel scheduler. But we are already running in parallel scheduler, and we consume a thread. And this monad.delay will never get executed because we already consumed all the threads, and now they are blocked and waiting for something. We can, of course, fix this code by decreasing the biggest counter of our range. And boom, 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 some seconds, and yep, completed now. We can even put a constant here, 5. And this test will pass. So the tests are passing, it works on my machine, we should push it to production, right? Yeah, but in production, our code will be running in a container with 2 CPUs, 3 CPUs, 4 CPUs, we don't know. And in production, it will immediately block the processing in your application. And the thing is how to detect it. We cannot just, yeah, maybe we could actually, it's even code consulting, but we could rent out our developers and they'll be reviewing your code and telling you, hey, this code is blocking, please don't do this. And you're like, oh yeah, I fixed and now it works, cool, thank you. Here are your money. But, well, it's not really efficient. Even worse, sometimes you cannot easily detect if the code is blocking or not. You just see some method call, and you have to know whether it's going to block or not. Instead, we need to find some way to automate it. And this is why we wrote a tool. It's called BlockHound. And BlockHound is another Java agent. So we are really into Java agents, as you can see. You can call it directly. You can use JUnit integrations. This is what I'm doing here. And now, if I run this code, we get an error. And the error says blocking call, sunmisk unsafe park. It's not even .await, because the issue is deeper, much deeper, down to the native methods of JVM. And apparently, to await something on a ledge, you have to park the thread. And if you open log support, then you'll find this code, unsafe park, time 0, like infinitely. So it's not even for some seconds, it's like infinitely. And now, after we call countdown, then this will unpark the thread and will continue. As you can see, we cannot even assume that we are talking about Java methods. We are talking about actually native methods, and Project Loom is currently focused on making these methods fiber blocking, and you will be running everything on fibers, not on threads, and it will park the fiber and not the thread. So after we have Project Loom, it's all good. But I really wish and I really hope that my grandchildren will be able to use the preview version of Project Loom, because it will take ages to adopt OpenJDK or just JDK in general, JVM, for Project Loom. And we still have a lot of code with Java 8 and even less, by the way. So yes, Project Loom will help. And this is your band-aid until Project Loom gets released. If you're curious, like me, most probably you want to know how it works. So I'll just quickly explain. It's not rocket science, to be honest. So let's say we have thread sleep. Classical blocking method, and one of the most blocking, reactive blocking code out there. Like if you see someone complaining about Reactor and something slow, then it means that he might have thread sleep somewhere or something else. So we have sleep, and then we rename it to BlockHound sleep, still native. And we create a public Java method instead. Now, the only thing we need to do is to add some magic. And this magic is check blocking call. If we focus on this check blocking, and as you can see, it's just one method call, one additional method call, or two, actually. So it can be used in production too, why not? But if we read about the blocking check, then how it works. First of all, we check if the current thread is already tagged or not. Tagging is a built-in mechanism in the JVM, and since check blocking calls a native method, we can easily access the internal mechanism of the JVM. So we check if the thread is blocking or not. If the tag is not present yet, we call the userland code and we call the predicate, hey, this thread, is it blocking or not? Because not every thread should be considered non-blocking. It's okay to have blocking threads, for example, main thread. You cannot run anything, like you have to block on something, or you run background threads, of course. But there are also blocking-friendly threads when we create a scheduler, let's say, for blocking calls. So we need to differentiate blocking and non-blocking threads. Now, if it's non-blocking, and it's super fast check. We walk this tech trace until we find a known method to us. And how it looks. Let's say we are at unsafe.park. So we detected that current thread is non-blocking. We detected that someone executed a potentially blocking or in fact blocking method. But now we need to decide whether we should or not throw an error. So next frames in this tech trace will be the ones related to the countdown ledge. And it's okay. We don't think that countdown ledge is blocking friendly, so we ignore them. Then goes some code where we executed this method. This is blocking code test, line 24 in our case, .await call. Now some reactor code. And now we finally get to the frame we were looking for. Because in the reactor integration, and by the way, BlockHound is not just Project Reactor project. You can use it with RxJava, with Akka if you integrate, with Kotlin when they integrate too. So anyways, in the reactor integration, we say that everything under wrapper.run must be considered non-blocking. So the outcomes. Blocking calls are bad. No surprises here. But what actually is surprising is that they may sneak into your production code and you will not even notice. Nobody cares how fast their tests are as long as couple of milliseconds. And okay, they run slow, maybe it's just testing. But in production, it will fail. So use BlockHound to detect the blocking calls, and that's the most important outcome of this talk. It must be, because it's such a pain to deal with blocking methods for everyone, for the users, for the framework developers, literally everyone. So do yourself a favor, just add it, make sure that it works and it detects blocking calls with some test where you check that, okay, if I have blocking call, it fails, oh good, expected. And then future you will, I don't know, will say a huge thank you. And you will not be debugging issue in production, performance issue, which is the worst kind of issues in production, I think, at night or something. And if you have blocking calls, please use a dedicated scheduler. With Project Reactor, it's super easy to offload some computation to another scheduler. Just run them in Elastic pool if you have infrequent blocking access, or some custom pool if you need to run a lot of blocking calls. Make your test pass with Reactor, and then it's all good. Some may say that, well, okay, I use asynchronous APIs already, and I'm safe, I'm protected. Well, yeah, that's true, or are you sure? I mean, it should be true, but that's the promise we receive, and yeah, pun intended, and we need to check if the promise is actually satisfied. Let's say we have Kafka producer send, asynchronous send, not just blocking send, but asynchronous. And we have a callback. And callback means Node.js, means some asynchronous processing, all good here. If you read the Java doc, it says that it will be running everything in asynchronous mode. So we have this asynchronous everywhere. Yeah. This issue is a known issue, and it's been reported more than 3 years ago, and people keep talking about the issue, and Kafka folks keep explaining that the only way to implement this method for some reason, but they are aware of this problem, and you should be too. So one of the outcomes of this talk, you come home and you realize that if you have Kafka in your application and you think that your processing is asynchronous, double check. And if you take a look in the sources, just out of curiosity, you'll find that there is code to wait on metadata, and metadata will call a wait update with max wait milliseconds, and by default it's 60 seconds. So if something is wrong with your broker, or some rebalancing is happening, or some other change to the metadata, then you may block your thread for 60 seconds. Oh well. Please always check your application, not just by reading the documentation, but make sure that you have enough tooling in your tests or in your staging environment or whatever, especially if you want to use the high-performance technologies like reactive programming or asynchronous programming. And last part of this talk, to apply the tooling, you may want to use Reactor built-in instrumentation mechanism, and I want to focus on them because we made it super easy to add tracing or instrumentation or whatever to Reactor. So first of all, in the latest release of Reactor 3.3.0.m1 was released last week, we have on-schedule hook. We have a bit more complex API in the previous version, but still. This is how it looks like. You add a hook, and for each runnable we are about to submit to some scheduler, we'll intercept it first, and you'll be able to capture thread locals, capture MDCs from your favorite logger, or do whatever you want, and then move them to the thread which will be running the task after you submit it to a scheduler, after we submit it to a scheduler. If you have tracing needs, or if you want to use MDCs from SLF4J, then you can use these mechanisms. Next one is on each operator. Remember the animation where I added a call after every basically after every operator? This one does the same. Without the instrumentation, without the bytecode magic, just it's built into Reactor. And when you run, when you add on each operator hook, then every operator you create, or your favorite framework creates, or whatever, every Project Reactor operator will be then wrapped into the function you provide. And if you're writing some library like, I don't know, Zipkin or something, or you have your custom tracing library, you can use this mechanism to move stuff and to instrument calls, because here you have access to every internal mechanism of Reactor. Basically, you create another publisher. There is also one for last operator, and we apply it when you call .subscribe, or when the framework calls .subscribe. It's also useful when you can do this as last call in the chain. Let's say you want to capture the current span ID or something. Not everyone is doing it, but apparently not everyone is using a well-known library for instrumenting GVM too. So some have their homegrown instrumentation libraries or tracing libraries, and can be helpful for them. So after the information I provided, I hope that your Reactor code will be looking like this. Yes, the fire may be dangerous, but also this is what keeps us warm. And once we realized how to keep the fire safe, we made a huge progress as humanity. So keep your fire safe, and be happy about your fire, and don't let it spread across your apartments. So I think someone taking photos, actually this slide will give you the same information basically with a bit less details, but the links. So please take a photo, check these links, and check the projects. And if you're using Project Reactor, that's something you definitely should at least consider trying. And if you want to learn Reactor, I hope I didn't made you think that you shouldn't. Actually, that's the other way around. And debuggability and development tooling of reactive libraries, such as RxJava, Project Reactor, Akka Streams, and others, is a big question, but also that's an undiscovered field. And we are just getting started with tools like these ones, and there are many more possibilities. So don't be scared of reactive code. Eventually, it makes your application performant and debuggable. Yes. So thank you. You can contact me in Twitter or GitHub or any other place you'll find me. Please don't Google me on Facebook. Just don't. And I'm happy to answer your questions if you have any. I'll check the fancy website. Oh, awesome. Cool. Question number 1 and top voted. When will Reactor debug agent be migrated to the main project, or is that not planned? It feels like my direct manager is in this room because he is asking the same question to me. And I'm happy to say that we do want to merge Reactor tools into the main project, and it will eventually become a part of Reactor core repo and also the project itself. Right now it's in incubating phase, but do expect it available in Reactor core mainstream. How do I close it? I don't, okay. If Reactor debug agent init is production ready with slight cost, why is it not the default? Everybody gets stack traces, few can, oh yeah, okay, and where some don't even have to pay the cost. And the answer is simple. The way it's implemented, it's a bit of an advanced technology. It also runs as a Java agent, and it may not work in certain environments. Although in most, it will work. And also, if you're running on Java 8, in current state of the project, at least you need to have GDK, not GRE. Starting with Java 9 plus, it's built in, so you can run with GRE, but with Java 8, you have to have the GDK. We'll simplify, we'll overcome it in future, but in current prototype, it is so. Then, as I mentioned, the project will eventually graduate from the incubator into the main project, and then we'll reconsider making it the default. But also, to answer the question directly, in Project Reactor, we do not enable things by default if we know that they will not cover 100% of cases or they will not work for everyone. Although it doesn't mean that you shouldn't be using it. It's just in the incubating phase, and also there are limitations at the moment. Can I use BlockHound in non-Reactor project, simple Java app? Yes, you can, and Project Reactor organization has BlockHound under it, but it doesn't mean that BlockHound is a project for Project Reactor. It's actually a generic project, a generic agent for any JVM workload, and you can use it already with RxJava. There is RxJava integration with Project Reactor. I should have a slide where I was linking an issue in Kotlin where they were considering adding BlockHound support to their coroutines, and you can integrate it with any framework you have as long as you have a marker for the thread, which can also be a pattern in the name, in the string, because you get a thread object as a parameter of the predicate, and some common differentiator of any stack trace. In this case, we were wrapping every runnable with a wrapper, just dummy wrapper. But yes, you can, and short announcement, I will be doing a series of articles about different asynchronous libraries in the JVM, and I'm not using reactors there, I'm just testing them for asynchronicity. Oh, Jesus, such a hard word. Anyways, I'm testing how async they are, and I'm just using completable futures. So if you're using completable futures, you can also integrate them with BlockHound. It's very easy to do. Is there any reason to use block delay methods? It's a bit hard to put them into the same category. if you mix blocking and non-blocking code, let's say you run Reactor to run some queries, but then eventually you return them from blocking framework and you need to get the result, then this is why we have .block method in Project Reactor. I'm not sure about the delay part, and you have 30 seconds to add a follow-up question so that I can answer it. But if not, then use the block methods only when you cannot use flat map, concat map, or some other reactive mappers. OK. No more questions. Thanks a lot for attending, and happy reactive programming and happy production experience. Thank you.